Okay, some more problems from section 9.5, and this is number 29. And this is our series. And again, it's an alternating series, but we're only going to just test it for absolute convergence, because we might get lucky, and if it converges absolutely, we're done. Okay, so this is an alternating series, so we'll test for absolute convergence. So we'll take the absolute value of this, which gives me 1 over 1 plus the square root of n. And as n approaches infinity, again, these ones in the denominators, they kind of become insignificant, so this really behaves like 1 over the square root of n. So let me try the limit comparison test, okay, and see what happens, because I know that this will converge because that's going to be 1 over n to the 1/2, and that converges by the well, that doesn't. That actually diverges, doesn't it? Because that's 1 over p to the 1/2. I'm sorry, 1 over n to the 1/2. So p would be 1/2. So that diverges. So let's see. Let's use the limit comparison test to see if they actually do behave like each other, and then we'll know it diverges. Okay. If not, I'll try something else. Okay. So 1 over 1 plus n, the limit of 1 over 1 plus n over 1 over 1 plus the square root of n, all over 1 over the square root of n. So this is what I'm going to check, that limit. Now if we invert and multiply, that just becomes the square root of n times 1 plus the square root of n. Now, I'll take the limit of this, and that's just going to be infinity over infinity. So what I can do is I can use L'Hopital's rule, and I take the derivative. If I take the derivative of this, I get 0, and then if I take the derivative of this, I get 1 over 2 to this times the square root of n. The derivative is this is 1 over 2 times the square root of n. So that's exactly the same. So that's going to be 1. The limit of 1 is 1. And remember, if that limit is between 0 and infinity, then they behave the same way by the limit comparison test. And we know that this diverges by the p-series test. P is 1/2, which is less than 1. So if that diverges, then this 1 over 1 plus the square root of n also diverges by the limit comparison test. All right. So therefore, our series does not converge absolutely. Okay. So let's go back and see what happens in its regular form without absolute. But we're going to test for conditional convergence. Does it converge but not absolutely? And remember, if you went the other way and you show that it converged, you still have to check to see that it doesn't converge absolutely, because it could still have absolute convergence, because absolute convergence implies convergence. So you still have to go back and do this anyway. So don't think this is the long way. Okay. And on these problems, we didn't have to, like 27, 28, 29, and 30. We didn't really have to do the 99th. Find the error, so I hope you realize that. Forgot to read my directions. Okay, for the new ones, 27, 28, 29, and 30. All right, so again, we're going to test this for convergence, and this is a alternating series. Okay, so this is my use of n term without the plus or minus part. And let's try the 3 criteria for the alternating series test. Is this greater than 0? Yes. 1 over 1 plus the square root of n. That better be greater than 0, because that's not defined. There's no way to make that negative. And is it decreasing? Yeah, it looks like is it decreasing? It looks like I add numbers to n. I'm going to be making the denominator bigger without making the numerator bigger. That's going to stay the same, so it's going to be decreasing for n greater than or equal to 1. And is the limit as n approaches infinity 0? I think you can see that. This gets bigger and bigger and bigger, so this is just 1 over 1 plus infinity, or 1 over 0, 1 over infinity, which is 0, so that's good. So it satisfies all 3 conditions, and you have to write those things down to show them. So it satisfies all 3 conditions for the alternating series test, the AST. So you can say, therefore, the series converges by the AST. Now, again, our directions were determine whether the series converges absolutely, converges conditionally, or diverges. Well, The series converges, but not absolutely, therefore it converges conditionally. Okay, it doesn't converge absolutely, but it does converge, so it would be conditional. Okay? All right, and one more. Number 30 here. The summation n equals 1 to infinity to cosine n pi. This is what I was thinking about when we did the earlier one of pi. Okay? I'm sorry, for sine. But that was just sine of n. This is n pi. So 1 pi, 2 pi, 3 pi, 4 pi, and you'll see what happened there. So this is going to be the same thing, okay, all over n times the square root of n. But this is the same thing as just negative 1 to the n, because if n is 1, it's pi, and the cosine of pi is negative 1. And if n is 2, it's 2 pi, and the cosine of 2 pi is 1. So it's going to go back and forth. So it's basically like an alternating series. And this is n to the 1/2 times n to the 3/2. So this basically is the same as this. It's an alternating series. So first we'll test for absolute convergence. And so we take the absolute value of that, which is just this. And this converges by the p-series test, because p is equal to 3/2, which is greater than 1, so it converges. So therefore, it converges absolutely, and we're done. If it converges absolutely, it converges. So there's no question of conditional convergence, as long as it converges absolutely, and this does. Okay, I hope that helps, and good luck.